Okay, so last time we were kind of talking about how to check whether one set is a part of another or equality of two sets. Okay, we talked about the different set operations. We had complementation, we had set difference, we had intersection, we had union, okay? One thing that we talked about last time is, sometimes it's convenient to draw a Venn diagram to sort of get an idea of why some of these things are true, yes? So in part A, one sort of intuitive way to think about this, think about it. A minus C, that means you take everything in A and just kick out the stuff that's in C, right? Well, A minus B minus C, that means you're starting with something less than A, yes? You're taking stuff away from A, starting with A minus B, and then removing C. So of course, that's going to be something that sits inside of A minus C, yes? It's kind of like, if you want to think about the subset or equal to thing, that's almost like a less than or equal to thing, right? It's almost like less than or equal to. And of course, if I have a couple of positive numbers, just think about positive numbers, A minus C is going to be greater than or equal to A minus B minus C, yes? You can kind of see how that would make sense on the level of numbers, but we're really talking about sets here, okay? Letter B, remember we talked about this one? If you go A minus C, you're getting rid of all the stuff in C, hello, yes? So there's not gonna be anything in C in that first part. A minus C has nothing with C in it. But the second thing, C minus B, starts with everything in C and then gets rid of stuff, yes? So in other words, this stuff right here, let me kind of write this down. This stuff right here is a subset of C, yes? C minus B, that's a subset of C, correct? But what about this stuff right here? What's that a subset of? That's a subset of A, of course, but it's also a subset of the stuff that's not in C. Does that make sense? Right, it's a subset of the stuff that's not in C because after all, I've gotten rid of the stuff in C, yes? This is supposed to be C bar right here, okay, C bar, okay? So look, if I'm trying to intersect stuff in C bar and stuff in C, what am I gonna get? Is there gonna be anything in there? No, there's no overlap at all. That's why that intersection is the empty set. Of course, we did that one rigorously. We also drew a Venn diagram, just trying to remind you of some of the things we've done. Any questions on that before we move on? Okay, I want to talk about some rules that we can take to the bank. Okay, this ought to remind us of some of the logic rules. What if I take A and I union it with the empty set? I'm going to get A right back. You know what I'm saying? What if I intersect A? Remember, what does U stand for, just to make sure we're all on the same page? Universe. What if I take A and intersect it with the universe? Well, hello. I'm going to get everything. I'm going to get A. Yes? Okay. Okay, so those are the identity laws. It should remind you of taking a number plus 0. Right? You should almost think of this as like A plus 0 equals what? Equals little a. Okay, you should think of this as A. Okay, what is this acting like? It's not plus, but A times what? 1 equals little a. Now, if you go take DLD, which is digital logic design, over there, they literally will turn logical operations and set operations into plus and times. They'll use plus and times for that, but they'll be doing it on sort of binary numbers, okay? Binary numbers that represent true and false, where true is 1 and false is like 0. Does that make sense? So they turn and into times, and they turn or into plus. But remember, the union operation is like or, correct? And the intersection operation is like and, okay? All right, the domination laws. If I take a set and I union it with the universe, what am I going to get? The universe, okay? If I take a set and I intersect it with, if I intersect it with the empty set, well, what are you going to get? The empty set, yeah? This one should kind of remind you of A times 0 is equal to what? 0, yeah. The other one, you know, it's not so clear, but at least that second one should remind you of that. The idempotent laws, idempotent is like a thing that's like fixed when you operate it with itself. Okay, that's the definition of an idempotent. When you operate it with itself, you get itself back. Okay, so like the number 1 is idempotent with respect to multiplication. You understand what I'm saying here? The number 1 is idempotent with respect to the operation of multiplication, because what happens when I take 1 times 1? I get 1. The element 0 is idempotent with respect to the operation of addition, because 0 plus 0 is 0. Okay? So here you kind of think about what's going on when I take an element and operate it with itself, either in the form of union or intersection. And both times, I just get I get the set right back. Yeah, a union is set with itself, I get it back. I intersect, set with itself, I get it back. Okay, finally, I hope this one's pretty clear. If I take the complement of the complement, what do I get? Same thing. Take a complement, that's everything not in A, and I take the complement of that. Whoop, that's going to flip me right back to A itself. This ought to remind you of taking the negation of a negation in logic, yes? Or taking a negative in mathematics, okay? Or in numerical operations, okay? Okay, any questions on these set identities? They're sort of straightforward things that ought to make sense to us, okay? Commutative laws. Is it clear to you that, by the way, in math, we don't always take commutativity for granted. Okay, so for instance, we know that if you take a number and add it to another number, in real numbers, that it doesn't matter what order I do that in, yes? 2 plus 3 is the same as 3 plus 2. That's called the commutative law of addition, okay? But it turns out there are some mathematical realms where that doesn't hold. You ever heard of a matrix? Okay. Turns out that if you take a matrix and multiply it by another matrix, there's no guarantee that if I flip the order of the matrices around to multiply, you're going to get the same thing back. What? True. Okay. You have to be very specific about the order in which you multiply matrices together. So commutativity is a special privilege. It's not always the case that commutativity holds. But with respect to union and intersection of sets, it does hold, which is nice. And that should make sense to us, right? A union B is the same thing as B union A. Same thing with intersections. Associative laws. Okay, you guys know what associative means? It means like it doesn't matter, like if I'm trying to operate 3 things together. You guys know that if I add 3 numbers together, okay, so Hannah, if I told you to do 2 plus 3 plus 4, how would you do that? 2 plus 3 is 5 plus 4 is 9. So you did 2 plus 3 first, and you add 4 and you get 9. Well, I'm weird. I grew up in Israel and I read stuff right to left, even numbers, which gets me into trouble sometimes, since all numbers are supposed to be read left to right. Okay. I would rather do 4 plus 3 first, and then add 2 to that. Well, guess what? Still get 9. That's the so-called associative law of addition. Doesn't matter how you group the things when you have more than just 2, you get the same thing back. So the associative law of addition, there's an associative law of multiplication, and there's also an associative law of unions of sets. If I'm trying to union sets together, it doesn't matter whether I first compute the union of A and B and then union that together with C, or do the union of B and C and then union that with A, yeah? Same thing with intersections. Okay, so those are the associative laws. And also there's a distributive law A distributive law. And I actually want to think about this one. Or actually, I want you guys to think about it for a few minutes. Draw a picture that verifies that these two sides are equal to each other. Okay, so you're going to have to draw, okay, remember the Mickey Mouse diagram? I called it the Mickey Mouse diagram, right? Here's the universe, A, B, and C, right? Okay, verify those two identities with someone next to you, okay? So first identify what the left side is and identify what the right side is. And what had better be true about those two things? They'd better be the same, yeah? So think about that for a couple minutes. All right, I heard some good stuff going on. Someone want to talk me through the left-hand side of the first distributive law, the left-hand side of the first distributive law. Where's B union C? Those two blobs together, yeah, so, right, like that. And then if I intersect that with A, what do I get? What do I get if I intersect that with A? So I heard someone say the word jelly bean. Kind of looks like that, right? It's that stuff right there, yeah? Make sense? Okay. And what about the right-hand side? Well, A intersected with B. Where is A intersected with B? All right, it's this football shape right here, yeah? And where is A intersected with C? This stuff right here, yeah? And I want to take the union of those two things. Hey, what am I going to get? The jelly bean. I'm going to get the jelly bean again. Yes? And, so there you go. That's why that one is equal. Let's actually talk about the second one too, okay? I'm going to have to erase this though. Okay, so let's talk about the second one. So here's the universe. Here's A, B, C. You guys know why I call this the Mickey Mouse diagram, right? I hope you do. Okay, it looks like Mickey Mouse, right? Okay, especially now that it's, we've got some black ears going on here. And look at that. You can even see kind of like the part in Mickey Mouse's hair right there, yeah. Okay, so let's see. A union B intersected with C. A union B intersected with C. Well, A is obvious, yes? And that's this stuff. Okay, A is right there. Union B intersected with C. Well, B intersected with C is like right here. Okay, it's all that stuff, yeah? So what do I get here? I get like this circle with this little appendage coming off right there, yes? Okay. A union B. Okay, you guys know where A union B is, right? A union B is all this stuff. Okay. There's A union B. Intersected with what? With A union C, okay? So intersected with A union C. Okay, well, that's interesting. Okay, intersected with A union C. I keep accidentally turning off my pen, okay? So I have the blue stuff. I want to see where the blue stuff overlaps with the blue shape overlaps with the green shape. And of course, isn't that just exactly in the red thing that we colored in before? Yes, it's A with that little appendage there, okay? Cool, that's the distributive law. So you can distribute a union over an intersection, right? You can kind of see what's going on here. A goes to here and here, and that's why, so you have A intersected with B, union, A intersected with C. Do you see how the distribution is actually occurring here? And the same thing, with, I can distribute a union over an intersection, right? So I'm going to get A union B, and then I'm going to intersect that with A union C. Okay, that's cool. I like that. I like those ones. They're cool. Okay. All right. Any questions on that? We already kind of know this, but De Morgan's laws. Okay, De Morgan's laws hold. So for instance, let's just kind of talk together for a minute about the Venn diagram version of the first thing. Okay, so here's the universe. Here's A, here's B. Okay, A union B complement. Where's that? Where's A union B, the complement of the entire thing? Where is that? Well, it's all this stuff, isn't it? Yeah. It's everything outside of the combination of those two circles. Okay, that's what A union B complement is, right? So that's A union, or oops, sorry. A union B complement, okay? But where is A complement? A complement is where? Well, it's all this, but it does include some stuff in B, yes? And where is B complement? Well, now I'm going to do this in yellow. Okay? And the question is, where do the yellow and the green overlap? And guess what? The yellow and the green overlap in the red. Yeah? Because here I'm asking for the intersection of those two things. Okay? So De Morgan's law works also for sets. And it works the same way it did for logic, which makes sense because we know that the union operation is like or, correct? And the intersection operation is like and. And we defined these sets and these operations on sets in terms of logic, correct? So it makes sense to us that De Morgan's law would still hold. Okay? What about these things I've called the absorption laws here, the absorption laws? Okay, A union, the intersection of A and B. Well, to see why these are true, we could actually just distribute, you understand? If I distribute that, according to the distributive law, what would I get? What would the first thing be? A union what? A union A, and then it would be intersected with what? A union B. Does that make sense? Okay, so oh, wait a minute. That's going to be unhelpful because like what's A union A? What's that? That's going to be A, and that will be intersected with A. Or hang on, intersected with A union B. Is that true? Yeah, that's interesting. What did we just actually show? You guys realize that A union A is just A, right? So that's interesting. That we did show something. We showed that this is actually the same. These are equal to each other, yes? And that's not surprising because they both happen to be equal to A. But what's the rationale for why they happen to be equal to A? If I take A union, A intersected with B, think about it, okay? If I take A union, A intersected with B, where's okay, A union with A intersected with B. But where's A intersected with B? It's that little football shape in there, yes? It's right here, okay? So am I getting anything new by unioning A with A intersected with B? Am I getting anything new at all? No, I'm just right back at A. Okay, what about A intersected with A union B? Okay, well, A union B is all this stuff, yes? Okay, and if I intersect A with A union B, what do I get? A, okay? But we actually already just showed by using the distributive law that actually these two things are equal to each other, interestingly enough, yes? But they both happen to be equal to A in the end, okay? What if I take A and I union it with its complement? What am I going to get? Everything. What if I take A and intersect it with its complement? Nothing, right? So if I union A and its complement, I get everything. If I intersect A with its complement, I get nothing. Yes. Well, I mean, it's just all I'm saying here is like, where's, okay, if this is A, where's A complement? Yeah. So if I union those two things together, I get the entire rectangle, yes? If I intersect those things, do they have anything in common? No, there's nothing in common. Yeah. Okay. All right, any questions on those? Hopefully these kind of make sense. Okay. All right. Here's what I want, right, this will probably be the last thing we have time for. And I think this might be the last, well, it's not quite the last thing, but it's pretty close. Talk to someone next to you, and I want you to actually use some of the properties we just came up with to prove that these two things are equal, okay? And my hint to you is to start with this thing right here, but you're going to take the complement of this, right? So it's saying, show that the complement of that set is equal to the other thing, yeah? So when I say these are equal, I mean that the complement of this thing is equal to the other thing, yes? Okay? So think about that. Don't draw a picture, just use some of the properties that we just came up with. Okay? Think about that for a couple minutes. Okay. So talk me through like how do we get started here? If I take the complement of this union, what can I do? Yeah, Colby. That's right. So use De Morgan's law. You negate A, which is the complement of A, and that union becomes an intersection. And it's going to be intersected with what, Colby? Okay, well, it's the, okay, so if I do it one step at a time, it's going to be the complement of that intersection, yes? And then what can I use again? I can use De Morgan's again on that thing. And if I do that, what is the complement of B intersected with C? B bar union C bar, yeah? And do you see that that's basically the same as the one down there? Technically, I would have to use the commutative laws, yes, to kind of flip some things around, but that's it. In fact, I could do that, right? So this is, if I commute and put the A bar on the end, that's legitimate. But then even within this set of parentheses, I can commute that union. Does that make sense? So that's the same thing as C bar union B bar. Yeah? And there it is. And so those things are equal by De Morgan, and applying De Morgan a couple of times, actually. Okay? All right. By the way, I just wanted to point out that you don't just have to have unions of two sets. You can actually use this notation, since you don't have to like write, sometimes you don't want to have to write this, union this, union this, union dot, 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 union some other thing at the end. You can just kind of write union, okay, I going from 1 to n, okay, or an intersection of several things as well, okay. It's legitimate notation for sure. And I think I'm actually going to stop right there. I have some things in here about, binary representations, but I'm not going to do that right now, okay? Turns out you can represent a set with a binary string. where you just kind of list all the elements, and you list all the elements in the universe, if there's a finite number of them, and then you basically put zeros and ones in slots depending on whether the set has an element or doesn't have an element. Does that make sense? But we're not going to really utilize that all that much. I just wanted you to be aware of it in case one day you go and become a theoretical computer scientist. But I'll sort of leave it at that for today. Okay, so again, if you have your test, you can turn that in now. Otherwise, you can upload it to the web.